So welcome back to Undergraduate Seminar. It's wonderful to have you here virtually and in person. Brent Pym of McGill University is going to talk about periods from pendula to the present. Thank you for coming out, Brent. Thank you for giving us this talk.
Thank you very much for the invitation. I was a graduate student at U of T. I have very fond memories of my time there, so I'm glad to have a chance to be back virtually for now. Before I get started, I guess many people in the audience might be considering applying to graduate school, so I just want to put in a quick plug for our graduate program. Montreal is a great city. We have a great department with lots of excellent faculty members and students. It's a great place to be, and I hope you'll consider applying. Okay, so what I'm going to speak about today is a topic which is quite an active area of research in mathematics right now, which is the study of periods. So mostly this talk will be based on a survey article that was written by Kontsevich and Zagier a couple decades ago. But to motivate the discussion, I want to go much further back in history and talk about pendulum. Okay. So I want to imagine that we have a kind of ideal pendulum. So I've taken the picture from Wikipedia here. So it's a rigid rod of length L. And it has a mass m attached to the end of it. The rod itself is massless, okay? And now the question is, if I set this thing moving, how long does it take to go back and forth? So it's a dynamics problem, so let's use conservation of energy. So the kinetic energy of this thing is the mass times the speed squared. So the speed is L times the angle theta, or rather the angular velocity, d theta by dt. That's the velocity. So ml squared d theta dt is going to give us the kinetic energy. And the potential energy, that comes from gravity. So if I lift the bob up by some amount, then I get a bit of gravitational potential. And if you work it out, the potential energy in this configuration is actually mgl cos theta, where g is the usual acceleration due to gravity. Okay, so let's imagine now that we take this pendulum and we drop it from rest at theta is equal to pi over 6. So I take it 1/6 of the way to the top and I drop it from there. So conservation of energy tells us that for all time, the total energy, which is the kinetic plus the potential, has to be equal to the energy it had when it started. So it started not moving at all, it was dropped from rest. So d theta dt was equal to 0. And on the other hand, theta was equal to pi over 6 at the beginning. And so cos theta was root 3 over 2. And so at the beginning, the energy was exactly this expression on the right-hand side. Okay, so now what I'm going to do, I want to find out how long it takes the pendulum to oscillate back and forth. So let me rearrange and try to write this formula slightly differently. So I just move things around and I write dt, the small change in time along the trajectory, in terms of d theta, the small change in angle. And this is the formula which you get. So now if I add up over a full oscillation of the pendulum, the little change in time, then I'll get the period of oscillation. Okay. So more formally, the period of oscillation is going to be the time it takes to go from theta is pi over 6 to minus pi over 6. And so I just have to integrate d theta, this expression, between those endpoints. Okay, fine. Well, this is some integral. And we can rearrange it a little bit. So if we make a trig substitution, this thing boils down to this expression in red times this constant out in front. So you see all the dependence on the parameters of the pendulum, they're coming from the length, and that's it. And the mass has dropped out. And what's left over is this red expression, which is some real number, which is given by a definite integral. So all you have to do is evaluate this integral, find out what this number is, and you figure out the period of oscillation. There's just one problem, which is that this is an integral where we don't have any clear path to actually figuring out what this number is. Okay, the value of this number is what it is. It is this integral. Okay, there's no more elementary expression for it. But one thing I want to point out is that it's a kind of simple integrand in the sense that it's like built, basically it's almost like a rational function. It's like a ratio of two polynomials. Okay, there's this root here. All the coefficients which are appearing are rational numbers. It's quite a simple expression when you think about it. Okay. So these are the kinds of integrals which we're going to discuss today. They're the so-called periods. So what is a period? It's a vast generalization of this one example. So a period, we start with polynomials in n variables whose coefficients are rational numbers. Okay, so this is the standard notation, q adjoin x1 up to xn. So for instance, this expression here, 5 over 4 times x plus x squared times y, that would be a polynomial in x and y with rational coefficients. Here's something which is not in q adjoin x. So if I take the variable x and I multiply it by pi, well, pi is not a rational number, so this does not count as one of our rational polynomials. And similarly, sine of x, of course, is not a polynomial, so it doesn't get counted either. Okay, and here's the definition which Kontsevich and Zagier proposed. They say that a real number is a period if it can be written in the following form. So I can write it as an integral which converges absolutely and has the following form. It's an integral of a ratio g over h over some domain d inside n-dimensional space. And here g and h are both polynomials as above, so they're rational polynomials. So this is a rational function with rational coefficients. And D itself is some domain in Rn, which is also defined by rational polynomials. So more precisely, I can take a collection of polynomials, Fj, and I look at the inequalities where, so I force Fj to be non-negative, let's say. And that defines some domain. Okay? So I can do this for some collection of polynomials F. All right, so this defines some region in Rn, and I consider integrals of this form, a rational function integrated over a region defined by polynomial inequalities. Okay, so that's what it means for a real number to be a period. It's actually going to be better, in some sense, to talk also about complex numbers. So a complex number has a real part and an imaginary part. We'll say that a complex number is a period if both its real part and its imaginary part are periods in the sense above. There needs to be no particular relation between the integral which defines the real part and the integral which defines the imaginary part. It's just that I can define them both by an integral. Are there any questions about this definition?
Can I be super nitpicky?
Okay.
Okay. Wait, so we want g and h to be polynomials, but in the previous thing, your h was a square root of a polynomial. Are square roots of polynomials?
Next comment is that there's an equivalent definition where you allow all algebraic functions, so that would include roots. Okay.
You knew I was coming, okay. You anticipated this nitpick.
Yes,
thank you.
So the point is, if you're clever about it, you realize that if you have an integral involving like roots and things, then you can convert it into something of the form above by just manipulating the domain of integration and so on. Okay, so there are some tricks. I'll show you some in a few minutes.
Thank you.
Okay, so let me give some examples of periods. Every rational number is a period. Why is that? Well, the number a could be expressed as the integral from 0 to a dx. Okay, if I really wanted to write it in the form of the previous page, I'm supposed to have a rational function. That rational function is 1. So it's 1 divided by 1. And the domain of integration is x is between 0 and a. So that's a sequence of inequalities involving polynomials in x. Two of the polynomials are constant, 0 and a. The middle one is just x. Okay, so every rational number is a period. The number pi is a period. Why is that? Well, pi, of course, is the area of a unit circle, a unit disk. And we can express the area of the unit disk as the integral, again, of the constant function 1 over the domain where x squared plus y squared is at most 1. That's the interior of the unit circle. So you see in this expression on the right-hand side, everything is exactly as before. I have a polynomial inequality and the constant function 1, so a very simple rational function. If I have any positive rational number, then of course I can ask about the square root of that rational number, which is some real number. I claim that this is also a period. Why is that? Well, like above, I can write the square root of a as the integral from 0 to square root of a dx. And okay, well, I can observe that the integrand is an even function, so I could double the domain of integration and integrate instead from minus root a to root a and divide by a half. Okay, but now the thing is that if x is between minus root a and plus root a, then x squared is between 0 and a. So this integral is actually the same as the integral over the domain where x squared goes between 0 and a, and then I integrate 1/2 dx. So coming back to Parker's question, this is an instance where we had a rational function, a rational expression, or roots rather, appearing in the domain of integration, but we could convert it to a polynomial just by some trick. Okay, another example of a period. If I have a rational number which is not equal to 0, then its logarithm, sorry, I guess I should have said positive, then its logarithm is a period. No, sorry, not positive, any non-zero rational numbers, excuse me. So log a is a period. Why is that? So log a can be expressed as log a minus log of 1. And, well, that expression we recognize. The fundamental theorem of calculus tells us that this is the integral, x goes from 1 to a of 1 over x dx. So log of a is expressed as the integral of a rational function over a domain defined by polynomial inequality. Any questions about these examples? All right.
So far, so good?
Pardon me?
So far, so good. I think we're
Okay.
good.
Thanks. Okay, so we give a notation, at least for this lecture, we'll call the set of periods this kind of script P. Okay, so P is the set of all numbers, all complex numbers, which are periods in the sense above. So what can we say about this set of periods? Well, one observation is that the rational numbers are a countable set. And therefore, actually the polynomials in arbitrarily many variables with rational coefficients are also countable, because you see, to specify such a polynomial, I need to specify the coefficient of every monomial, but there are only countably many monomials, just the different powers of the x's. So the polynomials form a countable set, but the periods are constructed just by choosing a bunch of polynomials, but only finitely many to define any period. And therefore, the set of periods has to be a countable set. Now, on the other hand, we know that the real numbers and the complex numbers are not countable. And therefore, somehow most numbers are not periods. So to say that number is a period is somehow a very special thing. And so there's a kind of hierarchy of number systems. You know, we start with the natural numbers, and then we build the integers by adding negative numbers. And then we build the rationals by taking ratios of integers. And then there are the algebraic numbers, which are the numbers that can be expressed as the root of a polynomial with rational coefficients. So like square root of 2, for instance. And arguing similarly to what we did for root A on the previous slide, you can show that the root of any rational polynomial is a period. So these all sit inside the set of periods. But there are numbers here which are not such algebraic numbers. So pi, for instance, is a period, which is not the root of any rational polynomial. On the other hand, there are bigger classes of numbers. So for instance, there's a set of numbers which are called the computable numbers. A computable number is one where you can give an algorithm to calculate the decimal expansion to arbitrary order. Turns out that every period is computable in that sense. So in principle, you can write down an algorithm to calculate a period to arbitrary accuracy. Okay, but actually most numbers are not computable. Most complex numbers are not computable. So there's this whole hierarchy of different classes of numbers. So an example of a number which is not a period would be Chaitin's constant. Chaitin's constant is something from computer science. It's somehow the probability that a random algorithm will halt and instead of going on forever. Okay. It's known that Chaitin's constant is not a computable number, and therefore it can't possibly be a period. But it's kind of a strange number. In fact, there are no proven what I would call natural examples of numbers which are not periods. So somehow most of the interesting numbers that we encounter in mathematics turn out to be periods for some reason. One important exception is Euler's number E, which is conjectured not to be a period. But I would point out that E is obviously a computable number because, well, we can write it as the sum of 1 over n factorial. And of course, it's not hard to write down an algorithm to calculate that number to arbitrary accuracy. You just sum the first so many terms of the series. Okay, so the upshot is that periods are quite special, but nevertheless they're quite common. So here's another example. I'm going to kind of go in the reverse direction this time. So let me start by considering this integral. Well, it's an integral of a rational function over a domain defined by polynomial inequalities, so it is a period. Okay, I claim that it converges. Well, fine. Very simple, dx dy over 1 minus x times y. So we're going to evaluate this integral. And to do so, we're going to use the fundamental theorem of calculus, Fubini, etc. So to evaluate the integral as an iterated integral, I'll integrate first with respect to x. So x goes between 0 and y. So I integrate 0 to y dx over 1 minus x. And then I have to multiply dy over y and integrate from 0 to 1. Well, this integral with respect to x is a familiar one. It's a logarithm of 1 minus y. So I just use the fundamental theorem of calculus. Okay. And so now I have to do something which is a little bit less familiar. I have to take the function log of 1 minus y divided by y and integrate that with respect to y. Now, I don't know about you, but I didn't see this one in my calculus class. And the reason is that this is an integral which doesn't have a name like logarithm. Its name is less familiar. It has a name, but it's less familiar. So let's try to do this instead by just computing the Taylor expansion. So logarithm of 1 minus y with a minus sign out in front has a Taylor expansion. It's the sum y to the n divided by n. And then I have to divide by y and integrate with respect to y. So when I do that, I get an antiderivative, which is a sum y to the n over n squared. I have to integrate this y to the n over y. That gives me a y to the n divided by n. So I have to take the antiderivative and evaluate it at the endpoints. And so when y is equal to 0, I don't get anything interesting. When y is equal to 1, I plug 1 in here, and I get the sum 1 over n squared. Does somebody know the answer? What is the sum of this series?
Yeah, you got a lot of
Pi squared over 6.
Pi squared over 6, yes. So famously, Euler proved this in the 18th century. So actually, maybe it's not so surprising now that this is a period because we already knew that pi was a period. Okay. But anyways, I think what's interesting is the kind of method which you use to get to this answer, converting this integral into an infinite series. Okay. All right. More generally, there are a bunch of famous constants which are periods. So among these are the so-called zeta values. So if I take an integer k, which is bigger than 1, then I can consider the number called zeta of k. Zeta of k is the sum 1 over n to the power k. You may recognize this as the definition of the Riemann zeta function. So I take the sum 1 over n to the k. And that sum converges. And so it defines a real number. And actually, yeah, this one also has an expression in terms of integrals, very similar to what we did before. So now there are just more variables, but it's basically the same procedure. You do this as an iterated integral, and at every step you examine the power series, and you integrate term by term, and you'll convince yourself that the answer is this particular series here. So some facts about these numbers. Euler proved shortly after he dealt with zeta of 2 that if you take zeta of any even integer, then what you get is a definite expression here. The notable feature of this is that it's a rational multiple of pi to the power 2m. Okay. So this b2m is a rational number called the Bernoulli number. So zeta 4 is a multiple of pi to the power 4, zeta 6 is a multiple of pi to the 6, and so on. So then you may ask about the odd ones. What about zeta 3, zeta 5, zeta 7? You may ask whether those can also be expressed in terms of pi. And there's a conjecture about this, which is that the answer is basically as a big a no as possible. So not only do we conjecture that the odd zetas cannot be expressed as rational polynomials of pi, in fact, the expectation is that if you consider pi and zeta 3 and zeta 5 and zeta 7 and so on, you get a whole collection of numbers. And it's impossible to find any polynomial with rational coefficients such that whenever you stick in a bunch of these zeta values, you get 0. So these do not satisfy any algebraic relations defined with rational coefficients. So from the point of view of the rational numbers, these numbers are very independent from one another. What is known about this conjecture is a bit, but not a ton. So remember, Euler proved these facts about the even zetas in the 18th century, and it was not until 1978, more than 200 years later, that it was known that zeta of 3 is not a rational number. More recently, the year 2000, there were some results. For instance, it is now known that infinitely many of the odd zeta values are irrational. But the funny thing about the argument is that it does not tell us which of them are irrational. It just tells us that infinitely many of them have to be irrational. And an even stranger statement is that of the next 4, after the one dealt with by Apéry, there's zeta 5, 7, 9, and 11. And it's known that at least one of those has to be irrational. But again, we don't know which one. Probably all of them, but anyways, at least one of them. And since then, I think there have maybe been some further results, but these are kind of the flavor of what's known about these so-called transcendence questions for zeta values. So these are considered very difficult problems. So the main thing that I want to talk about is the following question. Let's suppose that I have two numbers which I know are periods. How can I tell if they are equal? Well, in calculus, we learn some, well, maybe not obvious, but they're obvious to us now that we know calculus tricks. So, for instance, integrals are linear, they're additive. So, if I have a domain which is written as the disjoint union of two smaller domains, d1 and d2, then the integral over the union is the sum of the integrals. Okay. And similarly, if I integrate f plus g, I get the integral of f plus the integral of g. Okay. So these are some obvious facts which you can use to try to prove that two periods are equal. But of course, additivity is not going to get you very far. Something which will help you a bit more is the fact that we have a change of variables formula. So if I make a coordinate change in n dimensions, then I understand how the integral changes. Okay? There's the usual Jacobian determinant which gets involved and so on.
A little bit of a plug here for Math B41. We're going to do that in Math B41. That's a whole thing. It's great. It's magic.
There's Fubini's theorem, which tells us that if I have a product, then I can decompose the integral, right? So the integral of a product is a product of the integrals. And then, of course, there's the fundamental theorem of calculus, which is probably the most important of the obvious tricks. And somehow, if you think about it, everything you learn in calculus, at least when it comes to calculating integrals, is in one way or another a consequence of these basic facts. So, you may say, okay, well, what's a trig substitution? Trig substitution is a change of variables. What's integration by parts? Integration by parts is basically the fundamental theorem of calculus used in a clever way. So really, there's no other fundamental trick available. And so it turns out that people have thought quite a bit about this and come to the suspicion that these obvious tricks are the only possible reasons why periods would be equal. So more precisely, there's a conjecture, which is a version of a so-called Grothendieck period conjecture. And what it says is that if you have two periods which are equal, then you must be able to prove it only using the identities above and nothing else. So this is quite a very difficult and deep conjecture. The experts, I'm not one of them, but the experts, I've heard them say that they don't hope to see this conjecture solved in their lifetime. This conjecture is known to imply the previous conjecture I mentioned about the algebraic independence of the odd zeta values. That would be like one small implication of this much grander conjecture. Okay? So this is a very difficult problem. So let me give an example of Euler's formula. Zeta of 2 is pi squared over 6. You can prove this as follows. So let me write this zeta of 2 in a slightly different way. So if you use a series expansion, you can prove that this integral I've got on the right-hand side is equal to 3 times zeta of 2. Similar to the way we expanded before, but a bit different. And now you can look at this expression and realize that there's a change of variables. Which is a rational change of variables. So x is expressed as a rational function of new variables c and eta, and similarly for y. And so you make this change of variables, and now you observe that actually this thing now is in a form where you can use Fubini's theorem. It decomposes. There's an integral over c and an integral over eta, and it's just a product of those two integrals. But now these integrals are familiar because 1 over 1 plus c squared, its antiderivative is arctan of c. And so we can evaluate these using the fundamental theorem of calculus, and we'll get, well, each one of them is pi over 2, so this expression on the right-hand side is twice pi over 2 squared. And you rearrange that and you get Euler's identity. This is an example of an equation between periods. Pi squared over 6 is equal to zeta of 2. Okay. And we can prove it using the basic rules. Okay, so so far I've kind of been speaking about elementary things in the sense that once you have multivariable calculus, you can define what it means to be a period. Okay. But what people have realized is that if you restrict yourself to those classical methods, you're going to find it's very difficult to address these questions about periods, because somehow all you have are complicated formulae, and what you're missing is some structural principles which will help you to better understand how these numbers behave. So the toolbox, which is nowadays the key thing for studying periods, is what's called algebraic geometry. Algebraic geometry is very simply the study of shapes which are defined by polynomial equations. This is a huge topic which touches on many different aspects of mathematics, and the connection with periods is just one facet of it. But in some sense, the subject did grow out of understanding these integrals, 2 centuries ago. So what is the main object of study in algebraic geometry? It's a so-called algebraic variety. So I'll give you the definition of an affine algebraic variety over the rational numbers. It's very simply the set of solutions of a system of polynomial equations. So polynomial equations of the form f1 equals so on equals fm equals 0, where each of these functions f is a polynomial as before with rational coefficients. And you'll notice that I've put an asterisk next to solutions. And the reason is we have to be a little bit careful about what we mean when we talk about solutions, because our polynomials have rational coefficients, but of course we know that there are numbers which are like square root of 2. There are numbers which are solutions of polynomial equations with rational coefficients, but those numbers themselves are not rational. So we have to allow ourselves the freedom of looking at solutions which take values not in Q, but maybe in some larger field K. And for our purposes, we're mostly going to be considering the complex numbers. Okay, so I'll write x of c for the set of solutions of these equations where x1 up to xn are complex numbers. Okay. So the equations themselves, they only have rational coefficients in the polynomials, but I look at the solutions in the complex numbers. Okay. So for instance, we can consider the following example. Here's an algebraic variety, a very simple one. It's the region defined by the equation xy is equal to 1. Okay. So if I think of x and y as, say, real numbers, then I'm just plotting the hyperbola where y is equal to 1 over x. Okay. So that's a very simple example of an algebraic variety. What are its complex points? So the definition is that they're the set of pairs x, y of complex numbers such that x times y is equal to 1. Well, as I said, this is the graph of 1 over x. So every pair x, y of this form can be written as x, comma 1 over x, where x is a non-zero complex number. Okay. So at the end of the day, this set is just a copy of the non-zero complex numbers. Okay, so if I know x, then I know y as well, and conversely. So, so now we have to think about the picture a little bit differently, because well, complex numbers, they have a real part and imaginary part, so they correspond to points in a plane, and 0 is the origin in this plane. So x of c, you can think of it as space, which is given by a plane with the origin deleted. Okay, so I just puncture a hole in the middle of this plane. Okay. And more generally, I could take any other field and I could ask for solutions, and the same reasoning would tell me that the set of solutions is in bijection with the non-zero elements in K. And well, the non-zero elements in a field, they form a group under multiplication. So this algebraic variety X, which I've defined, has a name. It's called the multiplicative group, because whenever I look at its solutions over any field containing Q, I get the multiplicative group of that field. So, so that's what this algebraic variety looks like. Any questions about this notion of an algebraic variety?
Room looks good.
Thanks. Okay, so if we have an algebraic variety X, we can make sense of a special class of functions on this set X, the so-called regular function. What is a regular function? A regular function on X is very simply a function which you get by taking a polynomial and restricting it to the set of solutions of some other polynomials, which is our X. Okay, so X is expressed as the zero set of some polynomials, and F is some other polynomial. We restrict it to the set X, and we get a function on X. So let's go back to this example of GM. So it's the X is given by the equation little x times y is equal to 1. So there are obvious functions on here which pick out the x coordinate and the y coordinate. I'll call them x tilde and y tilde. Okay, those are polynomials in the variables x and y. And I've taken them and I've restricted them to this set of solutions, big X. I should say that the standard notation for the set of regular functions is this curly O of X. Okay, so that's what I mean. Now, if x times y is equal to 1 for every point in this, this variety X, then it means that the functions which pick out the x and y coordinates are equal up to taking reciprocal. So this function y tilde is 1 over the function x tilde.
Good.
I was just going to ask if you've done the mammogram thing.
Yes, I have.
Okay.
November 3rd.
Lisa?
Yeah, sorry. Sorry.
Yeah, thanks. Okay, so what does it mean? It means that to describe all the possible functions on this variety, well, of course, they have to be polynomials in x tilde and y tilde. They have to be restrictions of polynomials. So what it means, since y tilde is 1 over x tilde, that the algebra of functions is exactly the set of polynomials in x tilde and 1 over x tilde. So more precisely, it's the expressions of this form. They're linear combinations of possibly negative powers of x with rational coefficients. So that's what a regular function on this particular algebraic variety looks like. Okay, so once we have this notion of an algebraic variety, we can start to generalize some notions which you see in multivariable calculus. So one of the things you see in multivariable calculus is the notion of a line integral, where you take a vector field and you integrate it along a path to get a number. Okay, so this appears in electromagnetism and so on. So in algebraic geometry, we have a variant of this construction. And instead of a vector field, we integrate an object which is called a differential one form. Okay, so what is a differential one form? So I'm going to denote the set of all of these objects. Differential one forms are omega 1 of x. That's the notation. What does it mean for alpha to be a one form? Well, very simply, alpha is just a formal expression where I take a linear combination of these formal symbols, dxi, and with some coefficient functions, g. Okay, so I take a bunch of coefficient functions, g, which are regular functions on x. So they're just ultimately just some polynomials. And I multiply them by these symbols, dx. Okay? And that's what a one form is. That's all it is. It's just a formal expression. And then, for instance, if I have a function, which is a regular function, I can produce such a one form as the differential of this function. So it's like the gradient. I take the first coefficient, g1, to be df by dx1. I take the second coefficient, g2, is df by dx2, and so on. Okay? So it's just a tuple of functions, which is like the gradient of f. Okay, so these are the kinds of things which we're going to integrate. And then we need to explain what is the domain of integration. So the domain of integration is going to be what's called a path in x. So what is a path in x? Well, I can take the complex points of this algebraic variety x. So I take the solutions with complex entries. And then I just consider an arbitrary map from some interval a to b, into this set x of c, which is differentiable. Okay. So here's a kind of picture, cartoon picture. I have x of c is this surface, and I take a path which lies in the surface, and it has endpoints gamma of a and gamma of b. Okay. And now I can define a kind of line integral of alpha over gamma, where I just kind of formally plug in gamma. X of t is equal to gamma. So I evaluate gj at gamma of t, and I evaluate dx at gamma of t. And what this really means is I have an expression where I have gj of gamma of t. That's a function of t now. And d of xj of gamma of t dt, that's just some function of t again. So at the end of the day, what I get is actually just a function of t defined on the interval from a to b, which I can integrate. And this defines a number. So this is basically defining the thing so that the change of variables formula for integrals is correct. So if you've seen line integrals in vector calculus, this will hopefully look familiar. So again, let's look at this example of GM. So GM is the solutions of x, y equals 1. The complex points are the non-zero complex numbers. And the algebra of regular functions is the polynomials in coordinate x and its inverse. So what does a one form look like? Well, remember, a one form is supposed to be some function times a symbol dx. So all I can have is this kind of polynomial in x and x inverse times dx. And now I can ask what happens if I try to integrate this thing. So the domain of integration is supposed to be a path in the complex points. So the complex points, as I emphasized before, you can picture them as the complex plane with the origin punctured out. Okay, so that's this picture here. And now let me consider a path in this region, which is just a straight line path going from the number 1 to the number a. Okay. So I can parameterize that. And then on the other hand, here's a differential form, dx divided by x. That's a perfectly valid expression of this shape. It's 1 over x times dx. So I'm supposed to be able to define this integral. So what I do is I parameterize this path as gamma of t is equal to t, where t goes in the interval from 1 to a. And then I end up integrating 1 to a dt over t, which gives me log a as we saw previously. So of course that is a period. Another example, we could take the unit circle instead. So the unit circle wraps once around this puncture, and we can parameterize it using the complex exponential. Gamma of t is e to the it, where t goes from 0 to 2 pi. So if you've seen complex analysis, you probably know how to evaluate the integral dx over x divided over gamma. So you parameterize this thing. It's d of e to the it over e to the it. And then, well, you use the chain rule and you work it out. Well, this comes out to integral of I times dt. So at the end of the day, this boils down to 2 pi I. So these are two examples of numbers which are periods. So this is a period because it's an imaginary number, but its imaginary part is 2 pi, which is a period. And you can prove some important facts about these kinds of integrals. So there are generalizations of the theorems of vector calculus. So in vector calculus, you learn that if you have a vector field on some domain in R3, which is the gradient of a function, and you evaluate a line integral of this vector field along a path, then there's kind of version of the fundamental theorem of calculus, which says you just have to evaluate the function f at the endpoints of the path. And similarly, you show that if the curl of this vector field is equal to 0, then the integral is invariant under deforming the path. So here's a picture. I have two paths in dark blue. One is deformed into the other in a continuous fashion. If the curl of this vector field is equal to 0, then the integral along any of these blue paths is the same. So there's a generalization in algebraic geometry which says that if you have algebraic variety x and an algebraic subvariety, so it's just a subset which is cut out by further polynomial equations, then you can take a one form, so something which you can integrate on x, and let's assume that when you restrict it to y, you get 0. And on the other hand, you consider a path in x whose endpoints lie in y. So here's a kind of cartoon picture. We have x of c, and we have y of c. These are the complex solutions of the equations. And then I consider some path gamma, which moves around in x, but the key thing is that it starts and ends in y. Then two things are true. So first of all, generalizing the first statement above, if alpha is the differential of some function, so it's like a gradient of little f, then again, you can evaluate the integral by just evaluating f at the endpoints. And there's also an analog of the curl, which is something called d alpha. It's given by this particular expression involving the derivatives of the coefficients of alpha. So it's just a generalization of the curl operation. If the curl is equal to 0, then this integral is invariant under deformations of this path, as long as you keep the endpoints of the path inside of this subspace y of c. And there are higher dimensional analogs of this as well. So there's a notion of a generalized, or a differential k form, where this is supposed to be something which you integrate in over a k-dimensional object. So it has now k dx's, and you take linear combinations of those with some function coefficients, but with a funny rule that if you multiply dxj by dxl, that's the opposite sign from multiplying dxl by dxj. This is to account for orientations which you're encountering in vector calculus, for instance. And there's a generalization of the usual vector calculus derivatives, grad, curl, div, and so on, which is the so-called exterior derivative. It's given by a simple expression. And so if you have such a k form, and you imagine now you have a kind of k-dimensional space. So instead of a map from some interval, you have a map from a k-fold product of intervals. So that's like a square if k is equal to 2, or a cube if k is equal to 3, and so on. And then there's a way of defining the integral of alpha over this kind of hypercube.
Before we go hugely deeper on this, I just want to say all of this comes up in B41 and B42. It's super exciting to see this. This is in your future. I also want to say we have 5 minutes.
Yep.
There's people at the gates knocking.
Okay, great. Thanks. So I will wrap up quickly. So I wanted to say there's a generalization of the fundamental theorem of calculus, which is called Stokes' theorem, which I guess you'll see in 341 version of this. Okay, so the really important idea is in algebraic geometry, what we try to do is to make a list of all the possible integrals which you can write down, modulo this relation, which is basically the fundamental theorem of calculus. So you consider all of the differential forms which have the properties I put before. So the restriction to the subspace y is equal to 0, and this form satisfies d alpha is equal to 0. And then you somehow ignore the ones which are themselves derivatives of somebody else, because those are going to integrate to 0. So you define a rational vector space from these differential forms, which is called the de Rham cohomology. And at the same time, you define something which is called the Betti homology, which keeps track of the possible domains of integration. So this is again a rational vector space which has following construction. You somehow take formal linear combinations of subsets of the complex points whose boundary lies in y, and then you ignore the ones which are themselves boundaries of something else, and you ignore the ones which are completely contained in y. Okay, so these are some vector spaces, and the integration which we've defined gives a way to take an element in the de Rham cohomology, so that's like a form, and an element in the Betti homology, which is like an integration domain, and then you can pair them by integrating to get a number. So this gives a bilinear map. And a theorem is that every number which you can obtain in this way is in fact a period. So this is a much more sophisticated setup, but at the end of the day, the numbers which you obtain in this way are exactly the numbers of the type we described at the beginning. They're periods in the sense of Kontsevich and Sagier. So maybe I'll, since we're short on time, I'll skip right to the punchline, which is that there's a very modern idea, well, you know, it's a few decades old now, but the modern tool called the theory of motives. And the basic idea is that if you have such a pair of algebraic varieties, then you can study these vector spaces called the cohomology. And those things, they somehow control all of the information about the periods. So for instance, there are some beautiful results which say that if you have algebraic varieties satisfying certain properties, like imagine that you look at what happens if you solve the equations not in a field, but say modulo 2. And the combinatorics are controlled in a certain way, then you can prove that the numbers you get by such periods are generalizations of these zeta values, so they're called multiple zeta values. So there's a lot of current research which is going into understanding these motives and how they control the periods. And applications include particle physics, where calculating various quantities, you get these funny pictures called Feynman graphs, and each one of them corresponds to a period integral. And a new strategy is to use this theory to understand these calculations in physics. So with that, I will thank you very much for your attention, and I remind you again to please have a look at our graduate program. Okay. Thank
you. Okay, thank you very, very much for that presentation. We are going to move the seminar a little bit offline now. That was wonderful. That introduced so many crazy math. I enjoyed it. Thank you, Brent, for coming and speaking. Thank you for the online participants. Just a couple of bookkeeping things. Next week, we're going to be online only. We don't have this room booked next week. My apologies. After that, though, there are snacks. So after that week, we're going to be back in here. There'll be snacks, same time, same Zoom link, everything. Okay. Thank you, Brent. Be well, be well, be well.
Thank you.